Thank you. So yes, as you said, for laser blanking applications in the automotive industry. So it's a project that is funded by the European Union, and we're working on these laser blanking applications. So the objective of the laser web project is to be able to go faster with the laser technology and to be able to replace the standards solutions. So as you will see for laser blanking, it will be in competition with mechanical press blanking. And for that, we need to work on the different aspects of the process. So the process itself, but also the machine design and the programming and program optimizations to be able to go faster and to be more productive with the laser technologies. So in laser blanking, we are competing against the mechanical press blanking. As you can see here, there is a coil of material, and with one stroke of the press, we can produce one side panel of a car. This kind of process is very productive because the stroke rate of the machine is very high, but has little flexibility. So the objective that we have is to replace or complement the current technology, that is the mechanical press, with laser blanking technology that is much more flexible. We can easily change the shape of the parts, whereas with the mechanical press, we will need to rework on the toolings. The setup is quite fast also, and we can program all the elements, and so we don't need specific toolings for each part geometry. And we can also optimize the use of material from the coil, because we can have better nesting of the part geometries inside of this coil. The main drawback of the laser blanking compared to the mechanical press blanking is the productivity. So the idea is not to replace all the presses by lasers, but to combine both technology to keep the press blanking for high batch and large volume production, and to use the laser solution for medium to low production bytes, and when we need this flexibility to be able to change from one part to the other one very rapidly during the day. So laser blanking line, it's composed of different elements. First, the coiler, that is taking the coils and bringing it to the leveler. The leveler will make it flat, and then we will have a small loop before to enter in the laser cutting. If we compare to classical press blanking, usually this loop is much bigger and requires pits or civil work, because we need much more buffer of material before the presses. With laser blanking, we can have lighter solutions with a smaller loop before this laser cutting process, and then we need a stacker that should also be a flexible solution, because we want the complete line to be flexible so that we can change easily the production from one batch to the other one. And so we need also a stacker that is either a robot or a robotic solution to adapt to the blank geometries. You can see here a small video of what is a laser blanking process. So you see the laser cutting head that is cutting on top of an open hole so that the sparks can go down, and the coil is moving while the cut is being performed. So this is quite different from a classical format cutting machines. You see that we do not have those slats to support the part, but we have one band that is required to be able to move the material and the portions that are already cut within the skeleton of the coil. And you can see also in the video that we have two laser cutting heads cutting at the same time on the same moving coil. And so here you can see at the end of the line the skeleton and the parts that were taken from the skeleton. So compared to the classical cutting process, we have programming challenges because of these moving coils, and the fact that more than one cutting head is cutting at the same time on the same parts. And to increase productivity, one solution can be simply to increase the number of cutting heads that can process the material on the coil. So this is one solution, but it also reaches its limit, because when we have 2 or up to 3 laser cutting heads, then it's difficult to keep the balance between the working heads and to have them turned on all the time. Maybe one laser head will be waiting for the other ones. So within this European project, that is the laser web project, what we aim is to develop new technologies to be able to have faster machines, so to have higher accelerations, and we are targeting 6G of acceleration. And we can achieve this thanks to new innovative kinematic design and also the use of lightweight materials with composite fiber for all the moving parts, so that we can have a strong architecture with lightweights. We're also implementing online vibration minimization techniques, because in this process, the main issues are coming from the vibrations that are disturbing the cutting process, and also offline optimizations, as we have quite a lot of freedom in the pass planning and work repartition between the heads. And this can be used to first optimize the repartition between heads, and also to smooth the trajectories so that less mechanical strength is applied to the machine due to the tool pass. Then we are also working with a process, and Presidec and Marcus is a partner of the European project. And in that sense, we are working in the gap control. That is more difficult in this kind of application because the sheet is moving. We have motions also below it, so that we tend to generate vibrations. And we can also have internal strengths of the coils that are released during the cut. So we also need automatic detection of cut loss and sensors integrated in the cutting heads, as commented before, to be able to have online process monitoring. And then the idea is to have a stronger process with more resilience, because in general, the parts are not that expensive as a unit part. But what is expensive is to stop the complete production line because of one loss of cut, for example. So what is important in our mind is to be able to detect those failures in the process and to discard those parts without stopping the complete production line. And the end of the European project will be for 2026. So we plan to have new machine design by that time. So this project is carried out by a large consortium where 16 partners. We have 3 different technologies, but for the partners that are working with a laser blanking technology, we have in Spain, so IDEKO is a research center, and we are the main coordinator of this European project. Then Fagor Sate is a large player in the automotive industry, coming from the mechanical press sector and now implementing these laser cutting solutions also. The machines are controlled by the CNC from Fagor Automation, so that we have enhanced both the mechanical design of the machine and also the CNC controls that is adapted for those specific laser blanking challenges. Then in Germany, so Presidec is provider of the laser cutting heads and all the sensors and monitoring systems. We are working with ModelWorks that is performing optimizations of the toolpath geometry and nesting. And finally, in Czech Republic, with Compotex, that is a provider of carbon composite structures that is helping in optimizing the design so that we can have these lightweight solutions and reach higher acceleration speeds. So to conclude, in this European project, we have 3 main technologies. You have seen some information about the laser blanking. We are also working in micro drilling and HELA processes. All of them have the same characteristics of productivity, very high speeds, where we need to work on the different aspects, process, design, and optimization of the program to be able to reach this high productivity and replace more classical processes like the mechanical press blanking for this presentation of today. So thank you for your attention, and I will be pleased to answer some questions.